Hello there and welcome to Upper 6th Further Maths. Here we're looking at integrating polar curves so we can answer questions from exercise 5C. A lot of integration involved here, so make sure you're up to scratch on upper 6th of integration. So let's have a look at what we're going to do here. Now, just a reminder of integrating with Cartesian coordinates in the lower 6 of A-level maths. What you're effectively doing here, just to give you a little bit more detail on it, is you're taking a curve and you're finding the area in between points A and B. And when you do this, what you're effectively doing is you're working out the area of a bunch of rectangles added together. And as we make these rectangles a smaller and smaller width, this increases the accuracy of the area under the curve. To give you a bit more detail of this, what we're effectively doing here is if we refer to the width of the bar as the change in the x-coordinate, or the very small change in the x-coordinate, we use the letter delta to represent a small change. So it's a small change in the x-coordinate, and that will be multiplied by the y-coordinate to work out the area of the bar. And what we're effectively doing here is we are adding up the rectangle that can be calculated by the small change in x times y. That would be the calculation for the area of the rectangle, width times height. This bit here is the width. This bit here is the height of the rectangle. And then what we're effectively going to do is we're going to make the widths of the bars really, really small. That's what this bit at the front does. Now, as you go on to do maths at university, what you'll see is that when you combine a limit and a summation, you get an integral. So it's the integral of the height of the bar with respect to x. And that's where this formula comes from. It comes from adding together a bunch of rectangles where the widths of those rectangles get smaller and smaller and smaller. Now, we're not going to do exactly the same in polar coordinates, but something very similar. So what we're going to do in polar coordinates, which is different to Cartesian coordinates, is we're going to take a section of a polar graph, bound it by two angles, and then work out the area of that section here that's bounded by these two blue lines and the red curve here. And the way that we're going to do that, we're not going to be doing it with rectangles, we're going to be doing it with sectors, small sectors of a circle, where we have just a very small part of a circle with the same radius, different changing radiuses each time, and then very small angles inside here. So what we refer to these angles are, these small angles that have been divided up here, is delta theta, because we have theta as the angle, that's the unit of change, the theta angle, and delta, remember, is very small change. So it is a very small change in the angle for each of these different sectors. So to work out this total area, what we're going to be doing here is we're going to be adding up these areas of sectors. And remember from the second year of A-level maths, the area of a sector is equal to a half r squared, that's each of the radiuses each time we go to a new sector, times by theta. And in this case, it will be delta theta, because the theta angle will be a very small change in the theta angle. So this is going to be what it looks like here. It's going to be a limit as delta theta tends towards 0, and then add up all of the sector areas where the angle is a very small change in the angle of rotation round from theta 1 to theta 2. And as we make that small change in the angle, as we make that change in the angle smaller, we're going to get a more accurate answer for the area underneath this, this area bounded by this red curve here. And just as before, when you combine a limit and a summation, it turns into an integral. So instead of it just being y dx, it's a little bit more complicated this time. It's half r squared d theta. And generally we move that half to the front. So the region bounded by the two angles and the portion of the polar coordinate curve is a half integral r squared d theta. So So don't worry about remembering the limit thing and the summation thing, just remember that to find the area enclosed by a polar coordinate graph, it's this formula here. Let's just show you a quick example of this. If you've got, for example, the curve 1 plus cos theta, and you want to find the area enclosed by the angles pi by 6 and pi by 3, this area here, then the calculation you'll have to do is the integral of 1/2, it's always a half at the front, and then it's the integral. Then you've got to put your boundaries in, so your lower boundary will be pi by 6, your upper boundary will be pi by 3, and then of r squared, and where it says r squared, you need to find the equation of the curve and substitute that in. So it's 1 plus cos theta, all squared, that's going to be integrated. Expand the brackets once you've squared it, and then do the integration from there. So that's how you apply the formula, and that's what you're working out when you use this formula. So let's see it in action. The question is, find the area enclosed by the cardioid with the equation r equals a brackets 1 plus cos theta. So I think it's a useful thing to start off with would be a little sketch of the diagram. 1 plus cos theta on a polar coordinate graph will look like this. So if we've got to work out this whole area, maybe the best thing to do would be just to work out the top area and then double it to work out the whole area. So that's what we're going to do in this question. We're going to work out the top area and then double it to work out the whole area enclosed by this curve. So that will mean the alpha value, the lower boundary, will be 0, and the upper boundary will be pi. So then the angle will go from 0 round to pi, and it will enclose all of this area here, as long as we integrate with respect to, as long as we integrate 1 plus cos theta times a. So for this question, r is equal to a brackets 1 plus cos theta, alpha is going to be 0, and beta is going to be pi. And that will work out the green section of the graph here. So we'll now substitute the formula into the formula. So let's go for it then. So remember this formula. This formula actually is not in the formula booklet, so make sure you do remember it. So it's going to be half, and then we will substitute. In fact, before we do any substituting in, we know that we're going to have to double it at the end, so we might as well just get rid of this half here rather than writing down the half the whole way through and doubling at the end. Let's just double it now before we have to write halves everywhere. So let's now substitute in those values. So alpha was 0, beta was pi, and r was a brackets 1 plus cos theta. So r was that, beta was pi, and alpha was 0. Okay, let's get started on the integration now. Now the first thing to do would probably be to square it all. Just square your inside of the brackets there. And then you can probably pull the a squared out to the front. Now a here, a is not any letter that's important to the question. It's just a scale factor multiplier. Treat it as like the number 7. As if the number 7 was there, what would you do with the 49? You'd just bring it to the front. So bring that a squared to the front. Then multiply out the 1 plus cos squared bracket, and you'll get this expression here. Now this is where some key information and some good skill level of integration is required, because you're now going to be able to, you now need to integrate all three of these things here. Cos squared particularly is a difficult one to integrate. So to integrate cos squared, you need to use the cos double angle formula. Just a reminder that the cos double angle formula is cos 2 theta equals, there's 3 of them, but the one in particular I'm interested in is 2 cos squared theta minus 1. So just rearrange it a little bit and you'll get cos squared. And actually, if cos squared is equal to this expression here, it's actually easier to integrate this thing here. So we'll replace cos squared with this expression here. So that's what we'll do. We'll use the cos double angle identity, because they are equivalent and this is easier to integrate. Okay, so once cos squared has been replaced, and now it's chance to integrate. Before we do that, let's just tidy things up. So the 1 and the half, that will group together to give us 3 over 2. And now let's start integrating. So do the integration, and we open up a pair of brackets, and it's going to be bounded in between pi to 0, so that needs to go on the front. 3/2, that's just a number, so that integrated will just be that number times theta. Cos integrates to, well, let's just remind ourselves of the circle of differentiation, and we should be able to work it out. So that's the circle of differentiation. We use it in reverse to integrate. Cos will go backwards to sine, so it's going to be 2 sine theta. And then cos again, but it's cos 2 theta. Now, when it's cos 2 theta and you differentiate, you multiply the 2 to the front, but when it's integration, you divide the 2 to the front. So it's going to be cos move back round to sine and divide the 2 to the front. So it's going to be 1/4 sine 2 theta. The next thing to do is substitute in the pi and the 0 into the expression, and then do the subtraction. So substituting pi in, you get this for all of these three expressions. Substituting 0 in, you get this for all those three expressions. The majority of them are 0 here, you can see. So the answer to this question is 3 pi squared, 3 pi a squared over 2. And there we are, that's the answer. Remember, we doubled it at the start, so we don't need to double it now. So make sure you show full workings, even if it takes a while. These questions do take a while to go through. Make sure you're really good at integration before you get started on this chapter. Moving on to another question just for us to practice on, we'll find the area of one loop of the curve with polar equation r equals a 4 sine 4 theta. This is what sine 4 theta looks like. We just want to find the area of one loop. So start by sketching it, and you'll identify you'll have 4 loops. We just want one of those loops. So that will be bounded in between 0 to pi by 4. So on the boundary here, alpha is going to be 0 and beta is going to be pi by 4, and the equation is a sine 4 theta. So substitute it into the formula. Let's get going on the integration then. If we're working out one of these loops, it's going to be a half in between the boundary of pi by 4 to 0 of the curve squared d theta. So that's what's happened here. Let's now expand the brackets on the function. Bring that a squared to the front because that's just a constant term. And now we need to think about integration. Now, how are we going to integrate sine squared? Well, sine squared needs a cos double angle substitution as well. So cos 2 theta is equal to 1 minus 2 sine squared theta, but we want sine squared 4 theta, so we'll just rearrange, but then we'll replace theta with 4 theta. So this is what you get once you've rearranged it, but now we don't want sine squared theta, we want sine squared 4 theta, so all of the angles in this identity are going to have to times by 4, and what you'll get there is a half bracket 1 minus cos 8 theta. So this will be what we're going to integrate instead. It's equivalent, but easier to integrate. So let's get started on the integration for it then. So it's probably easier if we pull this half out to the front. So that would be 1/4 a squared, and then this expression here. Let's now do the integration. So 1 is going to integrate to theta. So actually do the integration, it would be theta. And then remember, if we use the wheel of differentiation in reverse, let's just draw it out, then minus cos theta will integrate back round to minus sine theta, and then you divide the 8 to the front because we're integrating, so it would be minus 1/8 sine 8 theta. Now we sub in pi by 4 to 0. Make sure you do this twice, so pi by 4 goes in, and then 0 goes in, but when 0 goes in, actually we get nothing, so just substitute pi by 4, and that would be fine. And then work out the answer in exact values, and you get pi a squared over 16, because this thing here will just be 0. So that's the answer of one loop, and if you were asked the question to work out all 4 loops, or the whole boundary, or the whole area enclosed by the curve, then probably the best thing to do would be just work out one petal and then times it by 4. So there we are. Make sure you're good at integration for this topic. So important points, you sometimes have to do a lot of rearranging and substitution before you integrate, and your calculator might not give you exact values, so you need to find them by yourself by manipulating fractions. Okay, the final example that we're going to go through here today is a question where we have two curves and we want to find out the boundary, so we want to find out the area bounded by both of these curves. So we want to sketch the curves, we've got that already done for us. Part B is find the polar coordinates of the intersection of these two curves. So before we get started finding this area bounded by both of them, we need to find what this point here is and what this point here is. And the way that you find the intersection of two polar coordinate curves is just by setting the radius equal to each other. Find the angle where the radius is equal to each other is a similar question. So let's now just rearrange and work out what theta needs to be for these two curves to be equal or intersecting. Cos theta equals 0.5. So it's either going to be pi by 3 or minus pi by 3. So using these values of theta, we can work out that the radius will be 2.5 at these points. You can plug pi by 3 into either of these two functions here, and you will get 2.5 as your radius value. So the answer to this question is 2.5 comma pi by 3, the radius goes first, then the angle, and the same for down here, the radius is 2.5, the angle is minus pi by 3. So we've done part B now, let's move on to part C, find the exact area of the finite region bounded by the two curves. So the region we're finding is the area highlighted in green, it's this area here that we're looking to find the value of. The best way to do this probably is just to work out the area of the top part and then double it afterwards. So just work out this area on the top here. Okay, so to work out the area on the top here, we need to first imagine that we have two separate sections. We'll divide them into two separate sections where we have the section from 0 to pi by 3 and then the section from pi by 3 to pi by 2. Because one section is bounded by the red curve and one section is bounded by the blue curve. So the first thing we'll do is we'll work out the green area, the area in between the limit of 0 to pi by 3, bounded by the red curve, and then secondly we'll work out the area that's been shaded in red, that's in between the limits of pi by 3 to pi by 2, bounded by the blue curve. So we need to do two integrations here, one for the green area, one for the red area. So we need to work out both of these and then add them together. So let's do the red area first. The curve is going to be the red curve here for the green section, and the boundaries are going to be between 0 to pi by 3. So alpha is 0, beta is pi by 3, and for the blue curve the boundary will be pi by 3 to pi by 2, and then the curve line will be the third line for this graph, which will be so the blue one, which is 5 cos theta. So we'll do the red one first, so we'll substitute all of these values into the formula. So because we're going to double it to get the bottom as well eventually, we might as well get rid of the half to start with. The curve is 2 plus cos theta, and so that's what we're going to integrate once we've squared it. So expand the brackets, and then remember that cos squared is easiest integrated when we replace it with the cos double angle formula. So that would be a half cos 2 theta plus half. Group some bits together before we integrate. And now we'll do the integration. So it's going to be 9 over 2 integrated to 9 over 2 theta. 4 cos will integrate to 4 sine, and then a half cos 2 theta. You divide the 2 to the front, so it's a quarter sine 2 theta. Then we substitute in the boundaries of pi by 3 to 0, and once we calculate that, substituting in 0 won't actually give us anything in this case. We're going to get 3 pi over 2 plus 2 root 3 plus root 3 over 8. And simplifying that, we'll get, group them up, 12 pi plus 17 root 3 over 8. So we'll make a note of that up here, that the red area, both of them on the top and the bottom, was this expression here. Now let's work out the area bounded by the pi by 2, pi by 3 and the blue graph. So substitute those in. 5 cos theta is the curve we need to integrate. So it'd be 25 cos squared theta. The easiest way of doing that to integrate cos squared we've seen is the cos double angle formula. Bring the 25 over 2 to the outside because we've got a common factor of a half here and here, and the 25 at the front as well. That would be the easiest thing to do there. Then now we need to do the integration. Cos 2 theta will be a half sine 2 theta, and 1 will integrate to theta. Bounded by pi by 2 to pi by 3, so substitute both of those in and do the subtraction. Carefully work each of these individual elements out, then expand the brackets and simplify. Don't work anything out in terms of decimals on your calculator yet. Just be super careful doing all the calculations, keeping it in terms of pi and root 3 because we want to find the exact value. So we've now got the area of the red parts, the green part and the red part of the areas bounded by the red curve and the blue curve. Now we just need to add these two things together, and I'm sure you can do this. Maybe you need a calculator, but here is the answer. We could simplify it probably. Divide everything by 2 on the top. So yeah, 43 pi minus 12 root 3 over 12. And there we are. That's the final answer for the area bounded by those two curves simultaneously. These questions are often worth lots of marks. Your calculator might not give you exact values for long sums, so you need to be able to deal with the surds and the fractions yourself. Great advice there. Okay, so your turn to have a go at this question here then. Phrased a little bit differently, we've got r equals a plus 5 sine theta. The area enclosed by the curve is 187 pi over 2. Find the value of a. Pause the video and give this lengthy question a go. Okay, so the first thing to do maybe is to draw a sketch of this curve here. Now, if we have a plus 5 sine theta, then the Cartesian curve of this graph here, if a is strictly bigger than 5, will start at that value a, go up by 5, down by 5, and then end back at a again. And given that we're going down by 5 but a is bigger than 5, we won't go over the x-axis, so nothing complicated will appear here. So it'll be a minus 5 up to a plus 5. So what will happen here on the diagram is it will start at a, then it will go out to a plus 5, a bigger value, back round to a down here. This would be a, this would be a, this will have a radius of a plus 5. And then we'll come down to a minus 5 down here. And then we'll come back round to a down here. Now I think what will probably be easiest here, if we just chop this in half here, would be to work out the right hand side first, double it, and then work out the left hand side here. So my boundary is going to be in between, the first boundary will be minus pi by 2. The second boundary will be pi by 2. And the curve is going to have equation a plus 5 sine theta. So let's substitute it into the integral then. It's going to be a half, but I'm going to double the area anyway, so actually there's no point in writing the half. It's just going to be the integral between pi by 2 to minus pi by 2 of the curve a plus 5 sine theta. So a plus 5 sine theta, and this will go in a squared bracket d theta. So the next thing to do will be to expand the bracket. So it would be a squared plus 5a sine theta. And then it's going to be 25 sine squared theta, d theta. Now remember that the easiest way of integrating sine squared is to use the cos double angle formula. So let's rewrite it out with that equivalent expression, leaving the other two bits as they are. A squared plus 5a sine theta. And then it's going to be plus 25 over 2 minus 25 over 2 cos 2 theta, d theta. Okay, the next thing to do now is to integrate both of these sections. So it's going to be a squared theta plus the integral of sine is minus cos, so it would be minus 5a cos theta. And the next part's going to be 25 over 2a, so theta. And the last part is going to be minus cos will integrate to minus sine, so it's going to be minus 25 over 4 sine 2 theta. Bounded by the values pi by 2 to minus pi by 2. Now let's move on to the next section here, so let's substitute these values in. It will be pi by 2 a squared. Then it would be, when we plug in pi by 2 into cos, I think we actually get 0, so that won't be anything. Then it would be add 25 over 4 pi, because we have pi over 2 and an over 2 here, so combine that will give us an over 4. Then when we plug in pi by 2, we're going to get sine pi, and sine pi is 0, so that won't give us anything there. So it would be this amount, subtract, substituting in minus pi now, so it would be a squared minus pi over 2. And then it's going to be plugging in cos of minus pi by 2, and minus pi by 2 will also give us 0, so there won't be anything there. Then for this bit here, it will be minus 25 pi by 4. And then plugging in sine for minus pi will also give us 0 as well. So this is our final thing when we have our values substituted in. 4 of them have come out to be 0, and I just haven't written those down. So the double negatives will cancel each other out, so that would be plus, plus, and plus. So when we add this all together, it's going to be a squared pi plus 25 over 2 pi. And this is apparently going to equal then 187 over 2 pi. And the question is now to work out a, so let's just get rid of the pi's from all sides. Let's double everything, so it's going to be 2a squared plus 25 equals 187. Take away 25 from both sides and we'll get 162. Divide both sides by 2, we'll get a squared equals 81. Oh, this is ending up quite nicely. So a is either equal to plus or minus 9, but we know that a is greater than 5, so then a must equal 9. Lovely, there we are. It's always a bit of a pressure situation when you're doing a whole big integration question live on a video, but there we are, we've got it done, and I'm pretty sure that sounds correct. So there we are, that's the answer for question 4. Hopefully that made sense. Skill in drawing polar graphs is really actually quite important for this question here. If you don't have the graph available, then knowing to split it in half vertically rather than horizontally like we did in a previous question in this video is really important to be able to recognize that. Your integration skills must be up to top scratch. If they're not, then maybe consider going back to a previous video from A-level maths and really practicing and honing your integration skills before coming here to work out some areas of polar curves. Alright then, hopefully you found that video helpful, and now have a go at questions from exercise 5C, all the problem solving questions, all the exam style questions, why not, to be able to really master this topic. Lovely, thanks very much for watching.